Okay, welcome back to the second video on Bernoulli's equation. So in the last video, we briefly talked about what Bernoulli's equation was and this general statement of energy conservation. And we also found out that this WEXT term, the external work, is the work done by external forces. And we had this giant tube of some kind of flow, and we cut out a very small section right here, which I've drawn down here. So this flow right here is our flow tube. So this is where the liquid or the fluid is passing through, points 1 here on the left and point 2 here on the right. So in this video, I want to continue on with deriving Bernoulli's equation. And in this video, we're going to look at the two external forces being applied to this system that I've drawn here. And we'll calculate the total work being done on this system. So there's work being done here at point 1 by the fluid to the left of point 1, which is all of this fluid here. And then there's also work being done on the right side at point 2, and that work is being done by all of the fluid on the right side of that pipe. Okay, so let's go back to our little diagram here. So at point 1, we have some sort of cross-sectional area here. So this is point 1. I'm going to label this A1 for area 1, and I'll just go ahead and delete this because we know that the flow is going to the right. And at point 2, we have what looks like to be a larger cross-sectional area. So this is A2. And the elevation at 1, I'll just label as Y1. So that's that little dot that I've drawn in the center of the cross-sectional area. And here on point 2, that is going to be Y2. Y2 I'll just draw here. So Y2 is, again, just the distance from our datum, which is this x-axis, up to that point. So this is Y2, and then this is going to be Y1. Okay, cool. So where do the external forces come from on this system? Well, remember up here I said that there was fluid here on the right and also fluid here on the left. Well, we know that inside of a fluid there is pressure. And when pressure gets exerted on an area, that causes force. In other words, we know that pressure is equal to force over area. So if there is pressure along this area, on top of this area, or acting on this area, we know that there's going to be some sort of force in that direction. Why? Because all of this fluid here on the right has pressure. It has internal pressure, and that pressure is acting on this area too. So we know that there's going to be a force acting here on area 2. And the same thing goes for area 1 over here. There's fluid to the left of this point, and there's pressure inside of this fluid. And that pressure is acting on this cross-sectional area A1, so therefore there's going to be a force acting on that area. So I'm going to label those as F1 here on the left, so this is F1, and on the right is F2. Now I did draw F2 acting to the left. Why is that? Well, because the fluid here is on the right, and that fluid has pressure. And that pressure is being applied to this area A2, so the force is going to be to the left. That is the external force acting on this system at point 2. Same thing for F1. All of the fluid here on the left has pressure, and that pressure is acting on area 1, so therefore this force is going to be acting to the right. Now you might be wondering, well, there's fluid inside of this system as well, therefore there is pressure inside of this system. Why aren't we including the forces due to those pressures? Again, that is because we are looking at external work being done by the system. So therefore the pressure inside of this system is really irrelevant, because those forces induced by the pressures inside of this fluid are internal. We're only looking at external forces being applied to this system. So that is why we don't consider the pressures or the force pressures inside of the system. We're only looking at the forces that are external. And again, if we're looking at the conservation of energy, this statement right here, it's only external forces, in other words, external work, only external forces can change the total energy of a system, not internal forces. Okay, so awesome. We now understand what the external forces are. Let's figure out what the external work is at points 1 and 2. And that is going to be the total work done, the total external work done on this system. So if at point 1 we have some sort of a force being applied to this area or to that point, we know that our fluid is flowing here to the right, so that work is going to cause some sort of a displacement in that point or that fluid. So on the left here, all of this fluid is going to be displaced, and here on the right, only a smaller section of that fluid is going to be displaced. Why? Because area 1 is much smaller, so the streamlines here are much closer to one another. In other words, the velocity of this fluid at point 1 is going to be much faster than the velocity at point 2, simply because the area is much bigger. So the streamlines would look something like this, where at point 1 they're very close to one another, but at point 2 you can see that they're spaced farther apart. Now we also know that the volume at these 2 points are going to be equal. So the volume of the fluid displaced here at point 1 over a very small amount of time is going to be the same as the volume here at point 2. So these 2 volumes are equal. Now on the left-hand side, this distance I'm going to call delta x. And on the right side, this distance I'm going to call, well, delta x, but delta x2. So this is delta x1, and on the right side is delta x2. So I know that the volume at 1 is going to be equal to the cross-sectional area A1 times delta x1, right? Area times distance gives us volume. And on the right, we have V2, volume 2, and that's equal to area 2 times delta x2, that distance of the fluid that got displaced. Now, you can see that this external force that I've placed at 1 and at 2, those are vectors, right? I've drawn the little vector symbol above them, and that indicates that whatever the magnitude of force 1 is, it's being applied to the right. And same goes for F2, that is also a vector. So this magnitude of F2 is, in this case, being applied to the left. However, the direction of this delta x1 and delta x2 are both to the right. Why? Because the fluid is flowing in that direction. So I know that when delta x1 gets displaced, this amount of volume gets displaced, it's getting displaced to the right. Same thing for delta x2. The amount that it's moved was, well, this distance, but it's moved to the right. So instead of calling these delta x1, I'm going to call this delta r1. And I'm going to put the little vector symbol on top of it to just denote that this is a vector and not just a magnitude, aka distance. Over here on the right, I'm going to say this is delta r2, and that's to the right. And with this, we can start calculating work. And I'm actually going to start that in the next video because that might take a little bit longer. But for now, understand this diagram. Over a very brief period of time, we have some sort of volume of fluid that gets displaced on both ends, and those 2 volumes are the same. Now at point 1, the fluid has displaced a delta x1 amount, which I'm just going to call delta r1 because the direction is to the right. And for point 2 over here, that amount of fluid that got displaced is, well, delta x2, which I just called delta r2 just to denote the direction. Finally, we have 2 different external forces that were being caused by the pressures of the surrounding fluid, so the fluid here on the right and the fluid here on the left. And with all of that, we can start calculating the external work being applied to this system. So we're going to calculate what W1, the work at point 1 is, and W2, which is the work at point 2. All right, so see you in the next video.